Okay, take 3. This is my 3rd time trying to film this review for you guys. So let's go ahead and take a look at it. This is the study guide for Chapter 3 for the upcoming test, and we'll also talk about this in our Zoom session. So we're going to look at solutions and solubility. Solutions are things that have something dissolved in it. So it has one material dissolved in another. Solubility is the dissolvability. How well does that material dissolve, and how does that change with temperature? Those are the things we're going to be taking a look at. So let's take a look at the definition of a solution. So the definition of a solution is when you have one material that is dissolved in another. So if you have something like salt in water, that would be a solution. Even cola or soda is a solution because the gases are dissolved in the water. So the difference between a homogeneous mixture and a heterogeneous one. So first of all, a solution is going to be what's called a homogeneous mixture, because the definition of a mixture is when you have a combination of substances. So you have a combo of substances or materials. So what is a homogeneous mixture? It's a combination of substances where, well, it's like a solution, where they're evenly distributed. So look at the word homo in the homogeneous. Homo means same. So a homogeneous solution is when your solution is evenly distributed. It's evenly distributed. An example of this would be salt and water, or just salt water. So salt water is a solution because one material is dissolved in another, but it's also homogeneous because it's the same throughout. Your salt is going to be evenly dissolved throughout. Another combination of substances would be a heterogeneous mixture. And hetero means different. That's when you have your two substances that do not combine evenly. They remain separate from each other. So a homogeneous mixture is going to be when your substances separate. An example of this would be oil and water. Your substances do not evenly distribute, they're not the same throughout, they remain separate. So contrast materials that are soluble versus insoluble. Soluble means that it dissolves. Insoluble means that it can't dissolve. So salt water, or salt in water, would be soluble. However, if you take the same salt and you put the salt in alcohol, we did this because we were trying to obtain the volume of salt, of the rock salt, and we put it in rubbing alcohol because it dissolves in water. So the salt in the alcohol is insoluble. Solubility, the definition of solubility is, the word that I created was dissolvability. And this is the amount of material that dissolves. And we'll take a look at that later. The amount of material that dissolves. So what happens to the amount of material that dissolves when you change the temperature, by increasing or decreasing the temperature? So solubility, we're going to say, is capital S, and temperature is going to be capital T. If you increase the temperature, what happens to the solubility? And when you decrease the temperature, what happens to the solubility? Well, we had this graph that I showed you, here's the temperature and here's the solubility. We're going to take a look at sugar, for example. And the graph looked something like this. When you increase the temperature and it got hotter, here's high temperatures, the solubility also increased. So increased temperature, high solubility. That means warmer temperatures are going to dissolve more of that material. This is the hot tea versus the cold tea, like the cold iced tea versus the hot tea. You can dissolve a lot more sugar in hot tea than you can in a lower temperature, where the sugar might just fall down to the bottom of the glass. So when you increase the temperature, you increase the solubility, you increase its dissolvability. When you decrease the temperature, it's colder, you decrease the solubility, you decrease its dissolvability. Let's take a look at an example of the solubility. Solubility of salt in water, the amount of material that dissolves. The amount that dissolves at room temperature is 36 grams. 36 grams of salt dissolves in 100 milliliters of water at room temperature. So let's say I add more than 36. If I add 37 grams in 100 milliliters of water, what's going to happen is I'm going to get 1 gram of salt left over. I put in too much. It can only hold 36, but I put in 37. That means 1 gram of salt is going to be insoluble. The 36 grams are soluble because they dissolved. 1 gram is insoluble because it can't dissolve. The water can't hold anymore. What can you do? Well, just like this graph right here shows, if you increase the temperature, you increase the dissolvability. So if you increase the temperature, what happens is the 1 gram dissolves. So that's solutions in solubility. Let's take a look at density. Noted between mass, volume, and how their units are measured. We're going to go ahead and draw this density triangle over here. Density is equal to mass over volume. The units for mass are grams, the units for volume are milliliters, and since density is mass divided by volume, the units for density are going to be grams per milliliter. What's the formula for density? Capital D is equal to mass over volume. And therefore, again, the units are going to be grams per milliliter. What will happen if the mass or volume is increased or decreased? We had various experiments that I want to remind you of. So again, the formula is density is equal to mass over volume. What happens if we increase the mass, and what's going to happen to the density? What happens if we decrease the mass, and what happens to the density? If remember, we had the film canister experiments where the volume remained the same. We didn't change that, but we did add pennies. And when we added pennies to the canister, the film canister sank. It became more dense. When you increase the numerator over here, you're going to increase your density. And when we took the pennies out, you're going to decrease the density, and it floated. What happens if we change the volume? Think of a hot air balloon. If you increase the temperature, what happens to the volume of the balloon? It begins to expand. Those particles start to bounce off each other with more energy. Increases the temperature, we increase the volume. Well, now we're increasing the denominator. Okay, going from 1/2, for example, to 1/3. I've increased my denominator, my value has actually decreased. So the hot air balloon becomes less dense, and therefore the balloon is going to float. Let's take a look example. If you exhale and jump into a pool, exhale and jump in a pool. What's going to happen to your lungs when you exhale? The volume of your lungs is going to decrease. Take a look at this. If we decrease this, it's going to increase your density. And therefore, when you exhale and jump into a pool, you're going to increase your density, you're going to then sink. Obtaining density, mass, or volume by rearranging the formula. Well, first of all, we have density is equal to mass over volume. Let's rearrange it for mass. Cover up the mass. Mass is equal to density times volume. And again, the units for mass will be in grams. What's volume? Cover up the volume. Volume is mass divided by density. That's how you do those types of problems. We look at buoyancy. Buoyancy is the capacity to float. So if I have higher or lower densities with positive or negative buoyancy and floating or sinking. So if I increase and have a higher density, increase my density, denser things are going to sink. Well, sinking is not floating, it's the opposite of buoyancy. So I have negative buoyancy. Also, if I decrease the density, less dense things are going to float. And if I float, I have buoyancy. Therefore, I have positive buoyancy. We did this demonstration with a canister and water. Why the canister floats when adding the salt. If you remember, we started with plain water. Here's the water. And I had a canister that had pennies, and it was on the bottom. So therefore, the density of the can is greater than the density of the water. Why is that so? Because it is sinking or has sunk. Things that are sink have a higher density. So this is more dense than the surrounding water. Then what I did is I took the water and I added some salt. So when you add the salt plus the water, well, take a look at the density formula over here. I'm adding more mass to my water, and if I add more mass, it's going to increase the density. So I increase the density of the water. So now, when we end, the density of the water is more than the density of the can. Meaning the can is less dense than the water. And what happened to that? It actually floated up to the surface. Okay, on to the next page. I'm going to take a look at the relative densities of solids, liquids, and gases. So, if you take a look at the density of solids and the density of liquids and the density of gases, we looked at a few different substances, and one of them that we looked at was aluminum. We looked at water, which was our liquid, and our gas is carbon dioxide. We did a lab on this. In our lab with aluminum, the density of aluminum was 2.7 grams per cubic centimeter. We did the water, where it's 1.0 grams per cubic centimeter. And the gas is 0.002. So this is larger than this number, this is larger than this number. The density of solids is greater than the liquids because they're packed into that crystal structure. Therefore, they have more particles per unit of volume. And gases have lots of space between them. So those are going to be the least dense. So we're going to calculate the density of a regular solid like a box. Imagine that the mass of the box is equal to 35 grams. And we want to calculate the volume. Remember, volume is equal to length times width times height. And let's say that it says that your mass is 35 grams and the dimensions of the box are 2 by 3 by 4. So we have 2.0 times 3.0 times 4.0. 2 times 3 times 4 would give us 24 cubic centimeters. What is the density of this? Density is equal to mass over volume. So my mass was given to us as 35 grams. The volume I had to calculate by multiplying length times width times height. So it's going to be 24 cubic centimeters. This would come out to be, my light just went off, 1.5 grams per cubic centimeter. Calculating density with an irregular solid with volume displacement. Okay, let's say that the mass of this irregular solid, like a rock, is going to be 20 grams. We can't measure the length and the width and the height, so we do volume displacement. So we get a graduated cylinder. We fill it up with 25 milliliters of water. Then we drop my rock, or whatever object, into the graduated cylinder, and it goes up to 35 milliliters. That means the object is the difference. So the volume is going to be equal to the 35 minus the 25. So my volume is 10 milliliters. What is my density? My density is equal to mass over volume. My mass was given at 20 grams. The volume I had to calculate by subtracting those two values, and it's going to be 10 milliliters. So my density is 2 grams per milliliter, or cubic centimeter. Calculating density of a liquid, as we did with water. So we're going to take a graduated cylinder. We're going to zero our scale. Going to zero that scale. Going to pour in 50 milliliters. Okay, so here's my volume, and it's going to weigh, after zeroing the scale, it's going to weigh 50 grams. Okay, what's my density? I'm running out of space, so let's go down over here. Density is equal to mass over volume. My mass is 50 grams. My volume is 50 milliliters. So my density of this material is going to be 1 gram per milliliter. It's water. Calculate the density of gas by weighing the mass change and collecting the volume of gas. This is what we did with the Alka-Seltzer. Calculate the density of a gas. Okay, if you remember the Alka-Seltzer, we weighed the Alka-Seltzer before, so we had the mass. We put the Alka-Seltzer in the water, and we collected the gas bubbles that formed, and we measured the volume of that. So you weigh before and you weigh after. So if you weigh it before and it's 95 grams, and you weigh it after and it's 83 grams, what happened to the mass? It went from 95 to 83. The mass went down. It was an open system, so the mass was allowed to leave. So we decreased the mass, and that decrease in mass is going to be equal to the mass of the gas that escaped. So we take 95 minus the 83, which is going to be equal to 12 grams. That's the mass of the gas that escaped. Let's say that we did the volume of this. We measured the volume of the bubbles and the volume of the gas bubbles that was collected was 45 milliliters. How do we get the density? Density is equal to mass over volume. My mass is 12 grams. My volume is 45 milliliters. And if you take 12 divided by 45 on your calculator, this will equal 0.27 grams per milliliter. Okay, down to these last few concepts. Know how temperature affects the volume and density of materials. If I increase the temperature, I'm going to increase the volume, just like a hot air balloon. And again, this is going to decrease the density. So looking at that formula, density is mass over volume. If I increase the volume, it increases the density. Again, remember examples. Let's say I have 1/2 and I go to 1/3. I'm increasing the denominator, but 1/3 is less than 1/2, so my density goes down. How does pressure affect the volume and density of gases? Remember, gases have lots of space, and these gases can be squeezed. This is the Cartesian diver. This is the bottle that was squeezed. And if you increase the pressure of that bottle, the little dropper on the inside is going to decrease the volume. So those gases inside the little dropper are literally going to get squeezed. So what happens? The density is equal to mass over volume. I'm decreasing my volume, therefore it's going to have the opposite effect on density. It's going to increase the density. And when you increase the density, your object is going to therefore sink. So you squeeze that air on the inside of the dropper, the volume goes down. To increase the pressure, we decrease the volume, it increases the density, and therefore makes that little dropper sink. So why does the Cartesian diver sink, or why it floats? This is the same thing that we discussed here, but let's take a look at the opposite. Let's say that we decreased the pressure. When you decrease the pressure, here we squeezed it, what happens is the air is going to, therefore, expand. So it's going to increase the volume. And when you increase the volume of the air inside of that little dropper, okay, looking at density equals mass over volume, density is mass over volume, I am going to increase the volume this time, it therefore is going to make it less dense, and less dense things are going to float. Be able to determine the number of significant digits. We will talk about this in our review, but make sure to see your notes, and we'll talk about many different more examples. Be able to add and subtract to the correct number of significant figures. So if you remember, when we're adding and subtracting for the significant figures, we actually don't use the significant figures. We use the least precise place value. Use the least precise place value. For example, if I'm adding 1.23 and 567.8, okay, when I add these two together in my calculator, okay, I get 569.03. Let's take a look. I've got ones, tenths, and hundredths. This is to the tenths place. This is to the hundredths place. This is very, very precise scale. This is least precise or less precise. So that means we need to have our answer can't be more precise than what is least precise. So my answer has to be to that digit right there. So I'm going to use the next digit to round up or down. And in case it's below 5, so therefore it's going to round down. So my answer would be 569.0. And yes, the 0 would be significant because it showed we measured to the tenths. Now, multiplying and dividing to the correct number of significant figures, we'll do a couple examples here. In this case, we use the least number of significant figures. Use the least number of significant figures. I'm going to abbreviate that. We'll do 2 problems and we'll do more in our review. We have 3.21 times 568.34. If I multiply that on my calculator, I get 18243.714. Question is, what will my correct answer be? This is a hard one. How many digits do I have here? I have 1, 2, and 3. So I have 3 significant figures here. I have 1, 2, 3, 4, 5 here. And I need to use the least, which means I have to round to something that has 3 digits. Well, if I go 1, 2, 3, here's my 3 digits here. That's as far as I can go. The rest of the numbers are not significant. They are insignificant. So I use this number to either round up or down, and it's going to round down. So my answer would be 182,000. Because if you remember, the zeros after a number before a decimal are not significant. So that would be my answer there. Let's do division. If I have 4.321 divided by 1.33456. If I plug this in my calculator, I get 3.237777125. So I've divided this on my calculator, I've gotten this answer, but now I need to count the number of significant digits. 1, 2, 3, 4. There's 4 here. 1, 2, 3, 4, 5. There's 6 here. So my answer has to be to 4 digits. So I'm going to have 1, 2, 3, 4. I'm going to have to either round up or round down based upon the next one. The rest of them are insignificant. So my answer would be 3.2, 3, and 7 is past the 5. It rounds up to 8.